Today's lesson is on Lewis dot drawings, specifically for elements. And Lewis dots are going to be used to represent electrons. And these diagrams are going to be very important because it's going to help us determine if a molecule is polar or nonpolar. What type of shape is the molecule? How many bonds does it have? Single bonds, double bonds? So Lewis dot drawings are really important for covalent compounds, which we're just starting with. So let's try some Lewis dot diagrams, and we're going to start with one element. So let's just do carbon first. So here's an isotope form of carbon, and we have here 6, which is also the protons, and because it's neutral, we have 6 protons and 6 electrons, and we also have 6 neutrons. But right now, we're really only concerned about the electrons. And we've talked about different models or ways to draw the electrons in an atom. And there was the old school way of drawing them, which was the Bohr model, which we know isn't accurate anymore. But here we have the Bohr model, which has 6 protons and 6 neutrons. Well, Bohr didn't have the neutrons, but 6 protons in the nucleus. And then 2 electrons, or 2 dots. And we're going to use dots for our Lewis dot also. 2 dots represent electrons in the first circle, the first energy level, and 4 electrons in the second energy level. Then we found out that life was a lot more complicated than that. We also found out that Miss Backus is not that great of a drawer. But here I tried to draw that. I have the nucleus with 6 protons and 6 neutrons. And then we have a 1s orbital, which would have 2 electrons. And then we have the 2s orbital, which would have 2 more electrons. And here I drew some 2p orbitals. And if you remember, that also looked like something more like this with the drawing, a little bit better than I could draw. We also drew electrons in this fashion called electron configurations. So for carbon, we would have written it 1s2, 2s2, 2p2, because we have 2, 4, 6 electrons. We also did box diagrams. So see, we've done many different ways to represent the electrons in an atom, and that's because the electrons are so important to the properties and so important to bonding. We have many ways to illustrate them. So the box diagrams look like this. We have 1s, 2s, and 2p, and we have 6 electrons, 1, 2, 3, 4, 5, 6. And we learned that they don't double up if they can spread out first. And here we had arrows representing electrons. Here we had superscripts representing electrons. So those are various ways we've done in the past for representing electrons inside of an atom. But when we talk about bonding, we don't really care about all the electron presence. We really only care about the valence electrons present. And the valence electrons are usually, because as of course always there's exceptions to the rules, but they're usually, and for our purposes here, the electrons in the outermost shell, and that's kind of the Bohr thinking, or as the modern view, the electrons that are in the highest energy level. And why do we care about just those electrons? Well, I'm glad you asked. That's because they're on the outermost edges of the atom. They're the ones that are going to be bumping into other atoms, and they're the ones that are going to be involved in bonding. So let's see what atoms do when they bond. So we're still talking about carbon. And so if we just looked at the valence electrons for carbon, we don't really care about the 1s orbital anymore. We only care about the ones in the highest energy level, and that would be 2. So we had 4 electrons in the higher energy level. We had 2 of them here and 2 of them here. Now you have to go back to the beginning of this unit to remember, the beginning of last unit, to remember our analogy of covalent bonding. And that was when we had the popsicle sticks. And you and your partner each had a popsicle stick. And you had a tug of war with them. And the covalent bonds were the ones that end up sharing the electron. One popsicle stick, which was an electron from you, and one popsicle stick from electron from your partner. And there we had some sharing going on. So to share electrons, the atom has to have 1 electrons to share. and then 2, a space for them to share them. And remember, we talked about that was one of the reasons noble gases did not react. That's because they had no place for any new electrons except a way far away new energy level. So let's look at carbon. I have 4 electrons here, but as it's written here, I only have space for sharing this one, and I only have space for sharing this one, because at the most I can only have 2 electrons in an orbital. So I can't share here, it's full, and I can't share here because it's empty, so I can only share here. Well, we find out that that's not exactly how carbon reacts, because we know that there are some common molecules. For example, CH4, which is methane gas. That's the gas that comes out of our gas jets that we use for our Bunsen burners. So we know carbon can bond with 4 things, and that's one of the most important things about carbon, and why it's so important to life is because it can bond with 4 different things, or 4 things, even though they're the same. So it can bond 4 times. But as it's written here, it looks like it could only share here and share here. So what happens to carbon? Well, just like we talked about in some of the exceptions for electrons, especially in the transition metals, when carbon bonds, it can make what we call a hybrid molecule. So instead of treating the 2s and the 2p as if they were separate regions, it treats it as it was one big set. Okay, so it combines it together. And just like electrons, when they were filling a set orbital, they would only go one in at a time before they doubled up. So if I think of the 2s and 2p together as an sp3, because there's 1 s and 3 p's, an sp3 hybrid, I can put 1 electron here, 1 electron here, 1 electron here, 1 electron here, and now I have electrons that I can share and space for electrons. So I could bond here, I could bond here, I could bond here, and I can bond here. So what does that have to do with Lewis dots? Well, let's take a look at carbon. So I am going to treat the edges of the carbon, so here, 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 and here, the 4 sides of carbon, as if they were the s, the p, and the p orbital. And instead of drawing arrows like this, I'm going to draw dots to represent electrons. So you will find that Lewis dots for elements are really simple. So I need to add 4 dots. And I'm just going to go around carbon 1, 2, 3, 4. Those are the 4 valence electrons, each separated because they can each go in an s and 3 of the p orbitals. So this is the Lewis dot for carbon. And this is going to be very important when we talk about bonding next. So what about other elements besides carbon? Well, first, to draw the Lewis dot, you have to know how many valence electrons they have. So I have to first count how many valence electrons. And once again, this is really pretty simple as long as you have a periodic table, of which you always get. So here's a periodic table. And we remember that the highest energy level is always going to be just the S and the P's, okay? Not the D's, not the F's. So here we have the first column on the periodic table has 1 valence electron. The second one, because that's in the S1 orbital, then we have 2 valence electrons in the second column. Then I skip the middle and I go here. I have 3, 4, we just did carbon, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7th valence electrons, 8 valence electrons. And this should be review because we talked about this on the periodic table unit. So very easy to count as long as we're skipping the transition metals, which have a lot of exceptions to the rules. So we're going to skip them for right now. But valence electrons, 1, 2, 3, 4, 5, 6, 7, 8. All right. So when I draw Lewis dots, I am going to put the element in the middle. So the X stands for the symbol of the element. And then I'm going to go around the element and put in dots. And I'm going to put in 1 dot in each of the 4 places. And it doesn't matter where you start. You could start at the bottom, you could start at the right, you could start at the left. It doesn't matter. I'm going to put 1 in each of these places before I double up. Now I put the boxes here, but they're not really present, but this is just to remind you this was like the S box, and this is one of the P's, another P, and another P. All right? So that's what, in theory, that's what they look like. I actually don't put those boxes on, so here's another view of it. So I have 1 electron in the first column. So this would be the symbol for anything in this first column. So hydrogen or lithium or sodium or potassium or rubidium or any of them in this column would look like this, except their element symbol would be in the middle. And so the Lewis dot says that here I have a lone electron here, and I can also form 1 bond because I could share here, which is most likely for hydrogen. So 1 electron, 1 bond, okay? Then the next column has 2 electrons, so I add another dot. And you can add this anywhere, it doesn't really matter, but as long as I don't double it up here first. So I have 2 dots, okay? Now I can form 1, 2 bonds. So 2 dots, 2 bonds. Then I go to the third column, which starts with boron, and I add another dot. So now I can form 3 bonds, 1, 2, 3. And you may be saying, but Miss Backus, I thought we were talking about covalent bonds, and the ones in the first couple columns, except for hydrogen, don't they lose their electrons? Yes, usually they do. So normally we don't worry about Lewis dots for them, but I'm kind of showing you in case there's some exceptions to these rules. We get up to carbon, we need to add 1 more dot. Okay, so that would be for carbon. And silicon and anything in this family would have 4 dots. And I can make 1, 2, 3, 4 bonds, right? And remember the X would be the symbol for the element. Now what about 5 dots? Well, now I have to start doubling up. So you could double here, just pick a spot to double up. So I have double up here. Now how many bonds can I form? Well, I have to share with something. So I can bond here, 1 here, 2 here, and 3 here. So I have 5 electrons, but here's looking for a partner, so I can bond here. This one's looking for a partner, I can bond here. This one is looking for a partner, I can bond here. This is a full orbital. Okay? Then I go to 6, which is in the oxygen family, the chalcogens, 6 electrons. So once again, I can really add it anywhere. And now I have 2, 4, 5, 6 electrons that are valence electrons. And I can bond here and here. So 6 valence electrons and 2 places to bond. So I'm hoping you're following this. And then here we have 7 valence electrons. So I double up again. And I have 7 valence electrons and now only 1 place to bond. All right. And then for our noble gases, they have 8 valence electrons and no places to bond, no places to share. Okay. So that's one of the reasons they're not very reactive, because no location to share, it's all full. The next electron would be in the higher energy level. So that's a generic way to look at Lewis dots. So let's just do one specific example. So here, what if I was going to do it for an element, and here the element is sulfur? So the first thing I have to do is find sulfur on the periodic table, and it's right under oxygen. And then I have to count what column is sulfur in. So this is the first, the second, I'm going to skip these, the third, the fourth, the fifth, the sixth. So it's in the 6th column, skipping the transition elements. And so I need 6 dots. So I draw them here, 1 on each of the 4 sides before I start to double up. 1, 2, 3, 4, 5, 6. So there is the Lewis dot for sulfur. I just have 6 dots, 6 electrons, and 2 places for bonding. So, hope you followed that. And if you have any questions, don't forget you can always ask me in class.